It used to be that a 2,000 pound an acre almond crop was enormous. These days, a 3,000 pound per acre crop is a realistic yield for a well-managed almond orchard. Of course, those yields don't come easy. It helps to start out with a deep, fertile soil or one in which you can easily manage your water and inputs. And you should also have varieties matched to local growing conditions. Then it's up to those managing the orchard to make sure that each tree gets the optimal amounts of water, nutrients, and protection against pests.
Is there a right way to grow almonds to achieve these consistent, bountiful harvests? Top agronomists in both private industry and universities are saying yes, especially when it comes to managing the very important nutrient nitrogen.
Of course, proper almond tree nutrition is complex and involves more than just nitrogen fertilization. Other essential nutrients, such as potassium, are also applied in high-yield almond orchards in conjunction with other nutrients, such as iron, zinc, and boron. And it goes without saying, proper water management is needed. Lately, there's been a lot of attention paid to nitrogen and nitrate, the form that can leach into groundwater. Many groundwater basins in the Central Valley are contaminated with nitrate at levels exceeding safe drinking water standards.
The State Water Resource Control Board responded by adopting the nitrate control program that is impacting every industry in California where nitrogen is used as input or waste discharges contain nitrate. Testing of groundwater basins in the Central Valley is finding that much of the nitrate contamination is attributable to applications to irrigated cropland of synthetic nitrogen fertilizers, compost, and animal manures.
Other nitrate sources are also contributing to groundwater contamination. Livestock, wastewater treatment plants for cities, and food processing plants.
Agronomists and researchers have devised a management approach for optimizing applications of nitrogen to crops to minimize leaching of excess nitrate while optimizing crop production. The approach is called the 4 R's: the right rate, the right time, the right place, and the right source. For almonds, the University of California, with support from the California Department of Food and Agriculture and the Almond Board of California, has spent years refining the 4 R's and now has many proven practices ready to be used today in California almonds.
Before going into details on the 4 R's, it's important to understand the relationship between soils, nitrogen fertilization, and irrigation practices. In particular, how nitrate moves in the soil and how it is taken up by a tree, essentially how all the science turns into management implications and tools.
A fundamental point to remember: any source of nitrogen applied as a nutrient can convert to nitrate. If conditions are right, nitrate can eventually leach beyond the root zone and into groundwater aquifers. Other factors are in play with nitrogen, such as soil mineralization, losses of the atmosphere, and biological processes. But leaching excess nitrate to groundwater is a major focus these days and deserves much attention. Excess nitrate is primarily a result of excess fertilizer nitrogen applied that's not taken up by the tree during the active growing season.
First, we have to understand why nitrogen is important for plants. Plants use more nitrogen than any other nutrient. Nitrogen is used in the tree's DNA and in hormones that signal the plant to perform certain functions such as cell division. Nitrogen is also a component of amino acids, which are used by the tree to make enzymes, which are also important for cell functions. Nitrogen is also critical for chloroplasts, which are the tree's sugar-making factories. When nitrogen is deficient in the tree, it can limit growth and cause leaf chlorosis.
On the other hand, excessive nitrogen applications can negatively impact yields. It can also cause excessive vegetative growth, especially in young trees. In those first 3 to 4 years, you want good growth but not extra vigorous growth. In mature almonds, excess nitrogen can increase susceptibility to diseases such as hull rot. Excess nitrogen also results in a higher risk of excess nitrate leaching in the groundwater. When thinking about nitrogen applications, you want to provide just enough to meet your yield demand in mature trees.
You also need to consider all the sources of nitrogen. Nitrogen provided by commercial fertilizers, nitrate in irrigation water, plus organic matter and residual nitrogen in the soil. Organic matter comes in the form of composted manure, green waste, or cover crops. When planting a new orchard, especially in rich soils, it's important to perform a soil test to ensure that the correct amount is available to the young trees. Under these conditions, additional nitrogen applications may not be needed until the tree starts showing significant growth.
Keep in mind that too much nitrogen in young orchards in particular can delay leaf drop in the fall, which delays the tree's transition to dormancy. This can leave a tree vulnerable to winter kill or frost damage. Excess nitrogen fertilizer can also lead to increased disease susceptibilities, so a key component of the 4 R's is the right amount of nitrogen. For almond trees 4 years and older, anticipated yield of the current crop is the primary factor impacting nitrogen demand, while in young trees, growth is the major factor to consider when determining nitrogen demand. Research has also shown that on average, an orchard extracts about 68 pounds of nitrogen per acre for every 1,000 pounds of nut meats. From year 7 and onwards, expected yield becomes the most important factor for determining nitrogen demand.
To determine the amount of nitrogen needed, it helps to refer to the table developed by the Almond Board of California. Multiply expected yield by 0.068. Don't forget to add in non-yield nitrogen demand, such as leaves and woody biomass. For an orchard 7 to 15 years old with a yield between 2,500 and 3,100 pounds per acre, you will need an additional 40 pounds per acre for non-yield nitrogen demand. That comes out to 210 to 255 pounds of nitrogen per acre. This amount assumes a 70% nitrogen uptake efficiency, which is typical for an almond orchard. Almonds might need a bit more nitrogen in years 2 to 5 as the tree is still actively filling its space, while also accounting for the nut load of those trees.
Researchers came up with these numbers by analyzing the nitrogen content in the nuts and shells and by measuring the amount of nitrogen in the tree structure itself. It's important to understand that trees take up nitrogen when they demand it. So in mature trees with a good crop set, the vast majority of nitrogen goes into the crop and a small amount supplies vegetative growth. The trees take up nitrogen throughout the growing season, starting at leaf out and continuing up to harvest. Currently, we have no evidence that almonds take up nitrogen after harvest. We want the right amount in the tree, when the tree needs it, and where it can get it.
To help understand how to effectively manage nitrogen applications, you need to understand the different forms of nitrogen in the soil and how nitrogen is taken up by the tree. There are basically the 3 forms of nitrogen in the soil: soil organic matter, ammonium, and nitrate. Soil organic matter is the nutrient storage bank in your soil. In the short term, organic matter nitrogen is tied up in big, complex organic molecules that are not immediately available to the plants. But over time, this organic matter breaks down and provides a steady supply of ammonium and nitrate to the soil and roots.
Plants can take up some amino acids directly, but these tend to be short-lived in the soil, especially in the warm, irrigated soils we have here in the Central Valley. Ammonium and nitrate are the forms of nitrogen that roots can take up. Being positively charged, ammonium can stick to soil particles, which are predominantly negatively charged, and hence does not leach easily. Nitrate is the other form of nitrogen that roots can take up from the soil. However, nitrate is negatively charged, so it cannot stick to soil particles, making it susceptible to leaching. As a reminder, when we talk about the cation exchange capacity in soils, we mean the ability of a soil to temporarily hold on to positively charged molecules. Ammonium is one of those positively charged molecules typically found in the soil.
How do these forms of nitrogen cycle through different forms in the soil? Let's start with soil organic matter. As organic matter is broken down by soil microbes, it releases ammonium. In warm, moist soils, that can occur in a matter of weeks to months, while in cold soils below 55 degrees Fahrenheit, this can be a very slow process. The carbon to nitrogen ratio is also critical. The higher the ratio, the slower the breakdown. Because this process is driven by microbial activity in the soil, it's very complex. As with all biological processes, it happens faster when moisture is present, when there is oxygen for the microbes to use, when temperatures are warmer, and when organic matter has a lower carbon to nitrogen ratio. When you apply organic amendments such as compost, you stimulate microbial activity, and these microbes require nitrogen and carbohydrates, both of which are present in composts. A good rule of thumb is that if the compost is less than 2% nitrogen, any nitrogen is going to be tied up by those microbes for a period of time until those microbes die. So, in organic systems, or if the compost is applied as a supplement to conventional fertilizer, it's important to understand the nitrogen content of the compost since its availability to the plant can be delayed until the compost breaks down.
Once nitrogen is in the ammonium form, it can then turn into nitrate through a process called nitrification. Nitrification is also microbe-driven, so the rate at which this occurs depends primarily on temperature. In California soils during the growing season, nitrification happens in a matter of days to weeks. As a consequence of this rapid microbial action, the nitrogen in soil organic matter converts to ammonium, which turns into nitrate and is leachable if it's not taken up by the tree. Same goes for fertilizer urea. It quickly converts to ammonium, then nitrate, which can leach if it's not taken up by the tree.
So how fast does nitrogen in organic matter and ammonium nitrogen turn into nitrate? At 50 degrees Fahrenheit, it takes 4 weeks for 40% of the ammonium present to convert into nitrate. At around 60 degrees in the top 2 to 3 inches of soil, 60% of the ammonium that you apply will turn into nitrate in 2 weeks if it's not taken up by the plants. At 75 degrees, it only takes 2 weeks for 100% of the ammonium to turn into nitrate. Now let's talk about how nitrogen moves into trees. Nitrogen uptake in trees is regulated by a number of biological factors. One principle to understand is that trees will limit nitrogen uptake when the plant already has all the nitrogen it needs. You can overapply beyond what's needed, and there may be some uptake, but there is a point of diminishing return since not all applied will be taken up by the roots. If a tree does have a need for nitrogen, the uptake rate may increase as the applied rate increases, but the tree will eventually reach a plateau and uptake maxes out. It gets to a bottleneck stage where you just can't get more nitrogen into the tree. It's already going as fast as it can. Translated to a management practice, this means spoon feeding a regular, applied smaller amounts over multiple applications. The more split applications, the better. You have less nitrogen sitting in the soil, waiting to be taken up by the tree, and vulnerable to leaching due to an accidental over-irrigation or poor distribution uniformity leaching nitrates from portions of the field, which all means that more nitrogen applied does not necessarily mean more nitrogen is taken up, and that it won't increase yields, especially if a tree was already at sufficiency levels.
All this science about how nitrogen behaves in the soil and in the trees has to be translated into practices for managing an almond orchard. Let's start with the right rate. Applying the right rate is about matching nitrogen supply with the nitrogen tree demand. That demand is all the nutrients a tree needs to build the nut meats, hulls, shells, roots, branches, twigs, and leaves.
This is our supply side: residual nitrogen in the soil, cover crops, manure, compost, and nitrate in the irrigation water, and synthetic nitrogen fertilizers, and even what's already in the tree, especially if there's a history of heavy applications in the past. Before we go on, let's talk a minute about nitrate in irrigation well water, or as it's being called, pump and fertilize. Years of research has shown that nitrate in irrigation water is available for plants to absorb and use just like any other source of nitrogen. An inexpensive well test can tell you exactly how much nitrate is in your irrigation water. Here's how to do the math. Take the test results, say 35 parts per million, and multiply by 0.227. Each part per million represents 0.227 pounds of nitrogen per acre per inch of irrigation water applied. That equals 7.945 pounds of nitrogen per acre inch of water. If you apply 36 acre inches or 3 acre feet of water during the growing season, the total is 286 pounds of nitrogen per acre per year. There is one more step. You need to multiply that 286 pounds times the crop nitrogen use efficiency. As a rough estimate, let's use 70% efficiency. At 35 parts per million nitrate and 70% efficiency, you should include about 200 pounds of nitrogen per acre in your overall nitrogen budget just from your irrigation water. Think of it this way: that's 200 pounds of free nitrogen applied to your crop. Better yet, you are helping clean up the groundwater aquifer.
Some of the nitrogen that isn't used by the tree can cycle in the soil, but generally any excess nitrate is susceptible to leaching into groundwater. And like a kid in a candy store, too much nitrogen results in luxury consumption by the tree, leading to excessive growth and higher susceptibility to disease. If too much is applied in a season, or even more than a tree can take up at a time, this can mean that you're spending money you don't need to spend on something the tree has no use for. So how do we arrive at the right rate?
5 years of studies funded by the Almond Board of California and the CDFA Fertilizer Research and Education Program took a close look at how an almond tree uses nitrogen fertilizers. The field work was done in Madera, Stanislaus, and Colusa counties. Analysis were taken of those orchards throughout the growing season, monthly samples of nitrogen contents of leaves, fruit, trunks, scaffolds, and roots. Samples were taken from 10 trees at each site over 3 years. When averaged over all 6 sites over 3 years, the result was 68 pounds of nitrogen was removed in every 1,000 pounds of marketable yield. So our right rate depends on the age of the orchard. For orchards 3 years and older, it's about 68 pounds of nitrogen per 1,000 pounds of expected yield plus the non-yield nitrogen demand. A fully mature tree that's 7 to 15 years old with a good yield demand is 40 pounds per acre. Non-yield nitrogen demand for young trees varies between 30 and 65 pounds of nitrogen per acre depending upon the tree age. Additionally, it's important to do frequent applications in smaller amounts to reduce the risk of leaching. The typical 3 to 4 nitrogen applications in a growing season can result in temporarily high soil nitrogen, leaving that nitrogen prone to leaching in subsequent irrigation or rainfall events.
Now let's talk about the right time. Keep in mind that a tree has biological bottlenecks called transporters that control nitrogen uptake into the roots, preventing uptake if there's no tree demand. Applying at the right time is about matching the timing of tree demand with root uptake. When is it too early to begin applying nitrogen? For almonds, soil nitrogen uptake begins at 70% leaf out. So when growth starts pushing during bloom and up to 70% leaf out, we know that all the nitrogen used by the tree comes from storage in the tree structure. So it's not worth applying nitrogen before 70% leaf out because roots are not taking up nitrogen yet, leaving it to potentially be leached by rain or irrigation. The same can be said for applying nitrogen during early leaf senescence or later when soil uptake diminishes to essentially zero.
Nitrogen fertilization can generally stop at or just before harvest. All this information is a result of numerous experiments conducted in orchards throughout California between 2008 and 2012. One of the best tools to guide your decisions on the right amount and right time is through leaf analysis. Leaf sampling results can provide valuable information to help you design a rational plant-based fertilization regime.
The University of California recently completed supporting research for leaf samples taken in April, which can be combined with a yield estimate to determine the nitrogen demand. Based on the work done over a decade ago by UC researchers, most California labs now have a method to predict July nitrogen values based on a complete leaf nutrient sample. Additionally, a July leaf sample can be used to monitor nitrogen status and make end-of-year adjustments. For most varieties, that's usually too late if growers want to use this information to determine their nitrogen budget. The April leaf sampling can be easily done following a few simple steps. First, note whether your orchard is generally uniform or has substantial variability.
If there's variability, take leaf samples from each zone. Areas that need more nitrogen can be separated by irrigation systems or can receive supplemental soil or foliar applications. Once the foliage has developed and it's between 35 to 50 days after full bloom, sample the leaves of 5 to 8 well-exposed non-fruiting shoots. Non-fruiting shoots will not have any nutlets. Select trees that are at least 30 yards apart from a minimum of 18 trees per orchard block if soils and tree growth are fairly uniform. If there are dramatically different soil types, subdivide the orchard into blocks based on the soil type and take leaf samples from each area. A minimum of 100 leaves per sample bag is required. Put all of your leaflets from an orchard block into a paper bag, mix them well, label the bag with an orchard identification, and send them to your nutrient analysis lab of choice as quickly as possible. Label all samples with collection date, field name, cultivar, and location within the orchard if possible. Note if foliar fertilizers were applied. If temperatures are warm, keep the leaf samples in an ice chest. Instruct the lab to analyze for nitrogen and also the other key elements of phosphorus, potassium, boron, calcium, zinc, iron, copper, magnesium, sulfur, and manganese. It's best to get a full leaf tissue analysis, not just nitrogen.
Results from all these nutrients will better guide recommendations if changes in applications are needed. Once you receive the leaf sample results, the nitrogen values can be input into the Crop Manage or CASP nitrogen calculators. The CASP nitrogen calculator advises on the timing and amount of fertilizer applications to meet yield-based demand. Also include results for other nutrients into your Crop Manage worksheets. Crop Manage allows you to compare your lab results to appropriate ranges. For the July-August samples, 2.4 to 2.8% nitrogen equals adequate nitrogen levels. Nitrogen below 2.4 indicates one of two things: inadequate nitrogen fertilization, which should prompt you to recheck your calculations of supply and demand, or nitrogen was applied inefficiently. If you suspect this may be the case, check for inefficiencies in placement, timing, or irrigation practices. Leaf sampling results can help you fine-tune your yield-based nitrogen management strategy to better match your crop yields to yield estimates, and it can highlight inefficient applications.
So where is the right place to apply nitrogen fertilizers? Applying in the right place means knowing where the majority of roots are and applying nitrogen where roots can best take up any nutrients and water as well. Typically, the vast majority of important feeder roots are in the top 18 inches of soil. During the growing season, roots will be the most active where water is abundant, usually the top 0 to 18 inches in the wetted irrigation zone. Roots will be shallower in young trees, and root depth will change as the tree grows. So, it's in that upper zone where you want to keep your water and nutrient applications. And remember, nitrate moves with water, so if you push water below the root zone, you risk pushing nutrients below the root zone as well. Active roots will always be in the same location that irrigation water is applied.
In flood-irrigated orchards, roots probably look like what you think of when you think of a tree root system, spread out and exploring a very large area. Root distribution in an orchard can vary dramatically if you compare tree-to-tree sprinklers and flood irrigation to high-efficiency systems such as micro sprinklers or double-line drip. However, it's important to remember that roots will be concentrated where the water is applied. That's why fertigation, injecting fertilizer during irrigations, is the most efficient method when using high-efficiency systems. All of the nitrogen is applied directly to an area with a high concentration of active roots. And speaking of fertilization, always inject the fertilizer at the last half or quarter of an irrigation set. That way the fertilizer isn't pushed past the root zone. Then stop the injection 10 to 15 minutes before the set is finished to ensure the system is adequately flushed.
As for the right source of nitrogen, there is no indication that the former type applied will impact yield or tree growth. The most widely and effectively used fertilizer formulations include urea ammonium nitrate, calcium ammonium nitrate, potassium nitrate, and ammonium sulfate. However, the short-term leaching potential can vary. Nitrate-based fertilizers are immediately at risk for leaching due to nitrate mobility, especially in sandy soils. Early research has shown that nitrogen stabilizers used with urea and ammonium-based fertilizers may slow the formation of nitrate, leading to less potential leaching. Ammonium is a positive charged form of nitrogen and will not initially leach. However, soil microorganisms rapidly convert ammonium to nitrate when soils are warm and moist. During the growing season, it can take only 1 week before 100% of ammonium is converted to nitrate, and nitrate is leachable.
Again, nitrate's negatively charged and can move through the soil very easily, so keep that in mind when choosing nitrogen fertilizer and managing that fertilizer application. There is a lot that goes into selecting the right source. In particular, how much do you want to spend per acre, what application methods used, broadcast or fertigation, through drip or sprinklers. There are many nitrogen fertilizer product options, but each has its own baggage. When choosing a commercial nitrogen fertilizer, consider how much and when the nitrogen is available for plant uptake. Calcium nitrate is a readily available form of nitrogen, but also has a high leaching potential. This leaching potential can be managed with well-timed applications, and calcium nitrate is well suited to fertigation systems. The calcium and calcium nitrate can also be helpful for managing soil salinity. Depending upon the rootstock, almond varieties can be fairly tolerant to salinity conditions. So it's important to review this information under the context of the type of rootstock that you are selecting for your orchard. For further information in this area, visit this website. Urea ammonium nitrate, UAN32, is very popular due to its solubility. The mixture of nitrogen forms makes this a slightly less leachable form of nitrogen, although in warm spring and summer conditions, the conversion to nitrate is very rapid. Additionally, urea is very leachable until it's converted into ammonium. An additional consideration is whether these fertilizers will acidify the root zone. Ammonium and ammonium-creating fertilizers will decrease soil pH. This can be a good thing if an orchard is in an area with high pH, high free lime, and/or sodic conditions. It can be a bad thing if you're growing an orchard in a light textured soil that has a low ability to buffer pH changes. When applying compost or manure, remember these materials need time to mineralize and convert to ammonium, making it plant available. Some of it can be measured in years. The release rate depends on how it's incorporated and the carbon to nitrogen ratio. We suggest you look up information specific to the form you are using at the following website.
Some agronomists estimate that about 40% of nitrogen compost is available in the first year after application, another 30% the following year, then the balance is released across several years. Research performed by the University of California suggests that there can be significant variability in those estimates depending on many factors, including the compost sources, the temperatures, soil types, and other factors. As for nitrogen content, compost averages about 3 to 4%. So if you apply 4 tons per acre, nitrogen available the first year would be about 96 pounds per acre. And remember, availability of the nitrogen from compost is very temperature dependent.
There are lots of reasons why you are making fertilizer choices, but always keep in mind the vulnerability inherent with each choice. The nitrogen budgeting tool, as part of the California Almond Sustainability Program, CASP, provides up-to-date coefficients to calculate nitrogen availability. In combination with the right rate, time, and placement, the right nitrogen sources optimize productivity and minimize nitrogen losses.
Finally, let's pull together a right rate, time, place, and source into one calculation. First, you have to consider yield history of each orchard, the current year growing conditions, conditions at bloom, and use that information as well as the results from your April leaf sampling to determine nitrogen supply and nitrogen demand based on your expected yield.
Knowing your tree age and expected yield, you can then use the Almond Board's table showing tree and yield progression with orchard age to determine total nitrogen demand. Nitrogen supply includes fertilizer, residual nitrogen in the soil, nitrate in irrigation water, and organic matter such as cover crops or composted manure. That's our rate. Then we get into the right time.
We know that when the nuts are growing is when the soil nitrogen uptake occurs. So we're looking at even applications starting at 70% leaf out and ending at or soon after shaking, depending on the cultivar you're growing. If there's residual nitrogen in the soil from prior years, that should also be considered. Then we are managing our irrigation to keep most of our water in the top 18 inches of soil.
Here is a summary of the takeaways from this session. 68 pounds of nitrogen for every 1,000 pounds of nut meats per acre, plus non-yield nitrogen demand. Don't put on more nitrogen than the plant is taking up and using. Following these steps will go a long way towards increasing your nitrogen use efficiency and decreasing nitrate leaching to groundwater.
Best of all, it ensures you get the most value from an expensive crop input. And in this farming economy, we all want the best return on every dollar invested.
For more information on fertilization guidelines, make sure to look at the Almond Board's resource on nitrogen best management practices. You can also go to the CDFA FREP guidelines and the Almond Board stewardship platform.